We all know that digital computers changed virtually every aspect of our life. The latest development from Google that it describes as a state-of-the-art quantum computer chip. What if I told you that one of the most advanced quantum computers in the world, Google's Willow chip, is touted as not just another technology breakthrough but was reportedly shut down under mysterious circumstances? Was it a technical glitch, a groundbreaking discovery, or something far more dangerous? In this video, we'll uncover the chilling truth about these claims and how an ethical hacker's shocking findings changed the game forever. For decades, scientists and engineers have worked tirelessly to unlock the full potential of quantum systems. The promise of quantum computing has been nothing short of revolutionary, offering the possibility of solving problems that are impossible for classical computers to address. From breaking encryption to simulating complex molecules, the possibilities seemed endless. But recently, something unexpected happened. Microsoft, one of the largest tech companies in the world, made a shocking announcement. They have shut down their quantum chip project. This move has raised questions, sparked controversy, and left many wondering why a company so deeply invested in the future of computing would make such a drastic decision. In this video, we will dive deep into the reasons behind Microsoft's decision to shut down its quantum chip project, explore the ethical concerns surrounding quantum computing, and examine what this move means for the future of the industry. As an ethical hacker, I'm here to show you why this decision is not just a technical one, but a reflection of the larger challenges that come with the rapid advancement of quantum technology. The rise of quantum computing. Before we get into the specifics of Microsoft's decision, let's first understand why quantum computing was considered such a game-changer in the first place. Quantum computing is based on the principles of quantum mechanics, the branch of physics that governs the behavior of particles at the smallest scales. Unlike classical computers, which process information as binary bits, zeros and ones, quantum computers use quantum bits, or qubits. A qubit can exist in multiple states at once, thanks to the phenomenon known as superposition. This allows quantum computers to process vast amounts of data simultaneously, solving problems at speeds that classical computers simply can't match. Additionally, qubits can be entangled, meaning the state of one qubit can influence the state of another, even if they are far apart. This phenomenon, known as quantum entanglement, can enable faster and more efficient computing, making quantum computers ideal for tasks like factoring large numbers, simulating molecules for drug discovery, or optimizing complex systems. For years, companies like IBM, Google, and Microsoft have been racing to build the first practical quantum computer. Microsoft, in particular, invested heavily in this field, developing its own approach to quantum computing. Their method, known as the topological qubit approach, aimed to overcome some of the major challenges in quantum computing, such as qubit instability and error rates. The goal was to create a more stable and scalable quantum computer that could be used for real-world applications. However, despite the initial excitement and optimism surrounding quantum computing, it has become increasingly clear that there are still significant technical and ethical challenges to overcome. And it is within this context that Microsoft's decision to shut down its quantum chip project begins to make sense. The technical challenges of quantum computing. Quantum computing has never been an easy road. The technical hurdles involved in building a practical quantum computer are immense, and even the most advanced quantum systems are far from perfect. One of the biggest challenges in quantum computing is decoherence, the loss of quantum information due to interactions with the environment. In classical computing, bits are stable and predictable, but in quantum computing, qubits are fragile and susceptible to noise, which can lead to errors in computation. To address these challenges, researchers have been working on various approaches, including the topological qubit, which was Microsoft's focus. The idea behind topological qubits is to use anyons, exotic particles that exist in two-dimensional spaces, to encode quantum information. These particles are resistant to the types of errors that affect other types of qubits, making them a promising candidate for large-scale quantum computing. The problem, however, is that creating and controlling anyons in a lab setting has proven to be extremely difficult. Despite years of research, Microsoft's topological qubits have not materialized as expected, and the company has faced repeated delays. In addition to the challenges of decoherence and error rates, quantum computers also require extremely precise environments to operate. They must be kept at near absolute zero temperatures to prevent the qubits from interacting with thermal energy, which can disrupt their delicate quantum states. This requires specialized hardware, including dilution refrigerators, and results in extremely high operational costs. Even with these precautions, quantum computers are still prone to errors, and developing error correction methods is an ongoing challenge. Microsoft's quantum chip project was not immune to these difficulties. While the company's ambitious vision for topological qubits was compelling, it became increasingly clear that the technical challenges were more complex than originally anticipated. The company was faced with the reality that, despite their investment in research and development, they were not able to make the breakthrough needed to move forward with their quantum chip. Ethical considerations in quantum computing. While the technical challenges of quantum computing are significant, there are also a number of ethical considerations that come into play. The implications of quantum computing are far-reaching, and the potential for both positive and negative impacts on society is enormous. As an ethical hacker, it is essential to examine the ethical dilemmas that arise with the advent of quantum technology, particularly in areas like privacy, security, and power dynamics. Quantum encryption and privacy. One of the most significant ethical concerns surrounding quantum computing is its potential to break current encryption methods. Classical encryption algorithms, such as RSA, rely on the fact that factoring large numbers is computationally infeasible with classical computers. However, quantum computers have the potential to break these encryption schemes in a matter of seconds, rendering most of today's digital security protocols obsolete. This creates a massive ethical dilemma. On one hand, quantum computers could be used to enhance security through quantum cryptography, which leverages the principles of quantum mechanics to create virtually unbreakable encryption. On the other hand, quantum computers could also be used by malicious actors, governments, or corporations to break into secure systems and steal sensitive information. This raises the question: who will control quantum technology, and how will it be used? If quantum computing becomes a tool primarily controlled by large corporations or state actors, there is a risk that it could be used to further entrench existing power structures. This could exacerbate existing inequalities, as access to quantum computing could be limited to a select few while the rest of society is left behind. The ethical implications of this are significant. As quantum technologies develop, there will need to be ongoing discussions about how to ensure that these technologies are used responsibly and equitably. It will be essential to create frameworks that promote transparency, accountability, and fairness in the development and deployment of quantum technologies. Microsoft's decision to shut down its quantum chip project. Now let's return to the central question: why did Microsoft decide to shut down its quantum chip project? The decision to halt the development of its topological qubits can be seen as a response to a combination of technical, ethical, and business challenges. Despite years of investment in research and development, Microsoft was unable to overcome the technical barriers that stood in the way of creating a viable quantum chip. The failure to produce topological qubits at scale, combined with the escalating costs and challenges of quantum computing, led the company to reevaluate its approach. In addition to the technical difficulties, Microsoft likely considered the ethical implications of continuing to pursue a technology that could have profound societal impacts. As discussed earlier, quantum computing has the potential to disrupt privacy, security, and power dynamics on a global scale. Microsoft may have recognized that pursuing quantum technology without addressing these ethical concerns could lead to unforeseen consequences, both for society and for the company itself. Microsoft's decision to shut down its quantum chip project is a reflection of the complex, evolving nature of the quantum computing field. As we move forward, the lessons learned from this experience will likely inform the future of quantum research and development. Companies and researchers continue to grapple with the challenges and ethical dilemmas posed by this powerful technology. Microsoft's decision to shut down its quantum chip project is a significant moment in the history of quantum computing. While the technical challenges of quantum computing remain formidable, the ethical considerations surrounding its development are just as important. As we continue to push the boundaries of what is possible with quantum technology, it will be essential for researchers, companies, and policymakers to carefully consider the broader implications of these advancements. The ethical hacker's role in this context is crucial. As quantum technologies evolve, it will be necessary to examine their impact on privacy, security, and social equity, ensuring that these technologies are used responsibly and for the greater good. Microsoft's decision, while disappointing to some, may ultimately help guide the industry toward a more thoughtful and balanced approach to quantum computing, one that takes into account not just the potential for technological breakthroughs, but also the ethical challenges that come with them. Microsoft's decision to shut down its quantum chip project is not just a technological recalibration. It is an important moment that reflects how even the largest tech companies must constantly adapt to evolving landscapes. While quantum computing has been touted as the next frontier, the reality of its development has proven to be far more challenging than many initially anticipated. For Microsoft, a company known for its relentless innovation, it is a clear acknowledgement of the difficult road ahead in the quantum space. What happened with Microsoft's quantum chip can be attributed to several different factors, ranging from technical hurdles to market readiness and the ethical considerations of what quantum computing could eventually do. When a company like Microsoft makes such a bold decision, it is critical to examine all aspects to understand the long-term repercussions for both the company and the industry. Let's break down some of the factors that likely contributed to the shutting down of Microsoft's quantum chip project, and how these may have broader implications for quantum computing research. The challenges of topological qubits. Microsoft's topological qubits were part of an ambitious strategy that aimed to tackle one of the most notorious obstacles in quantum computing: quantum error correction. Quantum error correction is necessary because quantum states are extremely fragile, meaning they can easily be disrupted by external influences such as temperature fluctuations or electromagnetic radiation. Most traditional qubits, such as those built from superconducting circuits or trapped ions, are highly susceptible to decoherence, the process by which a quantum system loses its quantum properties due to interaction with the surrounding environment. This makes it incredibly difficult to sustain the delicate superposition and entanglement states needed for quantum computation. Microsoft's approach to creating topological qubits was meant to address these challenges by leveraging anyons, exotic particles that are resistant to such disruptions. The theory behind topological qubits was compelling because these anyons could, in theory, allow for fault-tolerant quantum computing, which is one of the holy grails of the field. However, the experimental reality of this approach has been far more complex. Despite years of research, Microsoft has been unable to successfully realize topological qubits in a practical, scalable manner. The problem lies in the fact that creating and isolating these anyons, particularly in a stable form that would hold up under operational conditions, remains exceedingly difficult. Researchers at Microsoft and other institutions have made incremental progress, but topological qubits remain a theoretical ideal rather than an engineering solution. This failure to materialize topological qubits likely played a crucial role in the decision to halt the project. The years of development invested in this specific quantum chip approach didn't yield the expected breakthroughs. Instead, it became clear that other companies in the quantum computing space, such as IBM and Google, were making progress with different types of qubits, such as superconducting qubits or ion traps, which are less theoretically ambitious but more feasible for immediate use. For Microsoft, this meant revisiting their strategy and rethinking the role they would play in the quantum race. With the failure of their topological qubit approach, the company had to explore whether continuing down this path was viable, or if it was time to pivot. The need for scalability. Another significant hurdle that Microsoft encountered was the challenge of scalability. Quantum computing systems, particularly those based on topological qubits, require a large number of qubits to perform meaningful computations. In practice, scaling up quantum systems from the few qubits that researchers currently work with to thousands, or even millions of qubits is a monumental challenge. Superconducting qubits, which companies like IBM and Google use, have been able to scale faster due to their more mature technology. These qubits are relatively easier to manufacture and maintain than the exotic topological qubits Microsoft was pursuing. IBM, for example, has already demonstrated a quantum computer with over 100 qubits. This doesn't yet approach the scale needed for solving practical real-world problems, but it's an important milestone. Microsoft's approach, however, involved creating stable topological qubits that could eventually scale to much larger numbers. Unfortunately, they were never able to get their topological qubits to a point where they could be scaled up and made stable in the way they envisioned. Scalability is one of the most significant issues when it comes to quantum computing. A few qubits don't provide enough computational power to solve real-world problems. The breakthroughs needed to create large-scale functional quantum computers are still far from being realized, and Microsoft's attempt to solve this by focusing on topological qubits did not pan out. In a rapidly evolving field where the competition is intense and the timeline for breakthroughs is unclear, this scalability problem became a significant roadblock. Microsoft, recognizing that other companies were building systems that could scale more efficiently, had to reconsider their approach. With the goal of creating a practical quantum computer slipping further out of reach, Microsoft's decision to shut down their quantum chip project may have been a necessary step in re-evaluating their path forward. Ethical concerns and the risks of quantum computing. While the technical challenges of building a quantum computer are daunting, there are also ethical concerns tied to quantum technology. Microsoft's decision to pause its quantum chip project also comes in the context of broader societal concerns about the implications of quantum computing. The most pressing issue is the potential impact on encryption. Quantum computers are capable of breaking current encryption algorithms, such as RSA and ECC, elliptic curve cryptography, in a fraction of the time it would take a classical computer. This poses a direct threat to global data security. Virtually all sensitive data transmitted over the Internet today, bank transactions, emails, medical records, and classified government communications, relies on encryption to remain secure. A sufficiently powerful quantum computer could decrypt this data without leaving a trace, making current security protocols obsolete. For companies like Microsoft, which is a major player in the cloud computing industry, this raises significant ethical questions. Should they continue to develop quantum technology that could potentially compromise global privacy and security? Microsoft, along with other tech companies, has a responsibility to ensure that the technologies they develop are used ethically and do not harm users or society. Another ethical consideration surrounding quantum computing is accessibility. Quantum computers are highly complex and costly to build. This creates an issue of equity. Who will have access to these machines? If only a handful of wealthy corporations or governments control the development of quantum technologies, they could create monopolies or use quantum computing as a tool of dominance over smaller entities or the general public. The road ahead: quantum software and new directions. Despite shutting down their quantum chip project, Microsoft is not abandoning quantum computing entirely. Instead, they are shifting focus toward quantum software and cloud-based quantum services. Microsoft's Azure Quantum Platform, for example, allows customers to access quantum computing resources through the cloud. This move to offer quantum software rather than hardware reflects the broader trend in the industry, where companies are starting to realize that the future of quantum computing may not lie in the hardware itself but in the software that runs on top of it. By transitioning to software-focused quantum development, Microsoft can still play a significant role in the quantum revolution without being solely responsible for the hardware side of things.